Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Now, January and the early part of February is what we're calling I/O month. We're covering topics related to our I/O products. And for the next 3 weeks, we're going to do a series on some of the new aspects of OCS-I. OCS-I is our new family of expansion and remote I/O products that you can add to any Horner OCS all-in-one controller to add the amount of I/O you need, to put it in a different location, to add different types of I/O, whatever the case may be. All right, so let's take a look at our specific topic for OCS-I today. The OCS-I Universal Analog Input Module. Now, analog capability is certainly one of the strengths of the new OCS-I family, and to help us explore this new Universal Analog Input Module, we're going to bring in our product manager, Mr. Casey Gardner. How are we doing today, Casey?
Hey, not too bad. How's it going, Chuck?
It's going great. Now, anytime I bring you in as our product manager when we're talking about new products, I like to ask you about what you think are some of the kind of killer new features for a new product. So with this new Universal Analog card, what would you say is that killer feature?
Well, part of it's in the name. So in terms of the universal analog, that's something that we don't see a lot of in every market. Really the ability to have various different types of analog signals all just wired into one and configurable channel by channel. So a lot of times in the market, you'll get something specific to your different types of sensors, but maybe not the exact I/O count that you're looking for. So you may have an RTD module or a thermocouple module or an analog input module for milliamp or voltage or sometimes needed for each type. So in this case, we have one module that supports all of those types, which is really nice for a lot of our customers. And again, it was also expanding off of what we hadn't necessarily mentioned in this system was one of these inputs is also included on the base. So expanding that to 4 channels as well.
Very cool. So that versatility, the ability to take one module and put several different types of sensors into that one module could really save a lot of cost on separate modules, which you otherwise might have to invest in if you have a mixed sensor environment. Very cool. Now, from the standpoint of density, I know the ADU, which is the part number effectively, or at least the first part of the part number for this new module, is a 4-channel module. So do we have any plans on any other densities with OCS-I and analog?
Yeah, absolutely. So in the shorter term, we are definitely currently developing an 8-channel module that is going to specifically have milliamp and voltage support. So in terms of 4 to 20 milliamp signals and 0 to 10 volt signals, it's going to be configurable channel by channel as well. So that's going to be one we have in the short term. And again, if there's demand for it, there's definitely possibilities of more of an 8-channel universal in the future, but that's not currently on the roadmap.
Very cool. Awesome. So we're getting off to a great start with OCS-I and its analog capabilities, and we've already got some future enhancements on the way. All right. Thanks for that, Casey. All right. Let's take a look at how we're breaking down today's topic. We're going to start our program today by talking about some of the highlights of the ADU 100 module. A bulk of our time today will be spent going through the different signal and sensor types that are supported by the module. We'll give you application tips as we go, and then at the end, we'll show you how to configure the ADU 100, and we'll do a bench demonstration. All right, let's start with some of the highlights with specifications up first. There's 4 channels in the ADU 100, and it's built using a 16-bit A to D converter, which means it has plenty of resolution for most applications. It's quite accurate with a good specification of 0.2%. And as we talked about in the opening with Casey, it supports a whole bunch of sensor types from 4 to 20 milliamps or 0 to 10 volts, all the way to thermocouples, RTDs, and even millivolt signals. And as Casey mentioned earlier, one of the best things about the ADU 100 is that it is channel by channel selectable for the sensor that you're going to use, which makes it extremely versatile and economical. Okay, let's take a look at some physical highlights. Now, like all OCS-I modules, there are diagnostic LEDs available on the ADU 100. It's got a power LED and an OK LED, and then it also has 1 channel status LED per channel for a total of 4. And what causes that light to light up or to turn off varies by signal type. And we'll go through those as we go through the different signal and sensor types. Now, from a field termination standpoint, each channel on the ADU100 has 4 terminal connections, an A, B, C, and 0-volt connection. Those plugs are all removable. They're spring clamp style, so you can insert your wiring quickly, and you don't even need a tool to insert if you use ferrules. And all connections are labeled, which makes it easy to wire properly in the plant or in the shop. Let's start with the signal types of 4 to 20 milliamps and 0 to 10 volts. These are the most general purpose and the most common in automation. Examples would be pressure sensors, level sensors, sometimes even flow sensors, and there's literally thousands of sensors available that support these ranges. Now, when would you support 0 to 10 volts over 4 to 20 milliamps and vice versa? Now, generally, you should only choose 0 to 10 volts when it's the only output signal that's available for a particular sensor. Why would you choose 4 to 20 milliamps instead? Well, it has some advantages. First of all, if you have a sensor that fails or a wire that comes loose, you'll be able to detect in 4 to 20 milliamps that you've got a signal below 4 milliamps, which means you've got a problem. Whereas if you have a 0 to 10 volt sensor that fails, 0 volts doesn't really tell you anything because 0 volts is a valid reading. Also, from an electrical noise standpoint, 4 to 20 milliamp, because it's a current, that makes it much less prone to noise or voltage drop. Now let's talk about some application tips, and we're going to start with wiring. And we mentioned earlier that there are 4 terminals on each channel, A, B, C, and a 0-volt terminal. Now, depending on the sensor that's connected, you're going to find either the A, the B, or the C, or some combination of those will be used. So let's start with the 4 to 20 milliamp and the 0 to 10 volt wiring. And you'll see that the A and the B are used for current signals, and the B and the C are used for voltage signals. Now, why are there more than one 4 to 20 milliamp diagram there? Well, that's because there are multiple different types of 4 to 20 milliamp sensors. You have a 2-wire sensor, a 3-wire sensor, and a 4-wire sensor that are available, and they're all supported. One thing I will mention is this. These are relatively low-level signals, and you should use shielded twisted pair wiring between the sensors and the ADU100. That way, you can properly shunt any EMI or RFI to earth ground if you properly drain the shield for the cable. Okay, so don't cheap out. Use shielded twisted pair wiring. It's not that expensive, and it's the right way to do the application. Next, let's talk about the readings that come back. What format are they in? Well, remember, we're doing analog to digital conversion, so we're going to be getting a digital value back into our analog input register, and we have some choices as to how we want that data to come back. With the highest resolution, we can choose 0 to 32,000 counts. And if we just want real down and dirty readings that are easy to deal with, we can even do 0 to 1,000 as the range coming back. But we lose a lot of resolution in that case in exchange for what will probably end up being extremely stable signals. But all my charts here are assuming we choose the highest resolution available. And on the left there, I'm showing you how 4 to 20 milliamp readings come back. Now you'll notice that at 0 counts, that represents a reading of 4 milliamps, and 32,000 counts represents 20 milliamps. However, you can still detect values below 4 milliamps. They're just negative, all the way down to minus 8,000 counts, which represents 0 milliamps. So you can get high resolution by selecting the 4 to 20 milliamp range, but still detect under range or values below 4 milliamps. Now, if you choose 0 to 10 volts or 0 to 20 milliamps, you don't get quite the resolution with 0 to 20 milliamps, for instance, but you can detect all the way down to 0 with a reading of 0 counts correlating to 0 milliamps or 0 volts, and a reading of 32,000 counts representing 20 milliamps or 10 volts. So if you're talking current, I definitely recommend 4 to 20 milliamp as the range you should select. If you're talking voltage, of course, I still recommend 0 to 32,000 as the range you would select. Next, let's pivot and talk about RTD temperature sensors. RTDs stand for resistance temperature detector. They're definitely one of the most common temperature sensors that are out there, And today they're probably the preferred temperature sensor in most applications. That's because RTDs have several advantages. They're quite accurate, they're quite easy to work with, and nowadays they aren't really all that expensive. Early in my career, they had a reputation of being very pricey, but maybe with the proliferation and manufacturing upgrades, maybe that's caused the cost of RTDs to come down. Now, the only real disadvantage to RTDs is the fact that they have a limited temperature range. So if you're talking about reading temperatures above about 800 degrees Celsius, you'll need to use a different temperature sensor like a thermocouple, for instance. But that's really one of the few disadvantages of RTDs. Next, let's talk about how RTDs work. RTDs are simply variable resistors where the resistance changes with temperature. And there are several types of RTDs that are available, and those types are defined by the material of construction and the resistance value at 0 degrees C. Now, the most common RTD sensor type is a PT100. PT stands for platinum because that's the material of construction, and the 100 means that the reading for a PT100 at 0 degrees Celsius will be 100 ohms. Now, 100 ohms is a relatively low resistance value. And if you have a significant amount of wiring between your measuring instrument, like the ADU100, and your temperature probe, then you might have a few ohms of resistance in your lead wiring. And a few ohms of resistance, if it's not compensated for, will cause an error in the reading. So any quality RTD measuring instrument, like the ADU100, will have the ability to work with 3-wire and 4-wire RTDs. And what the measuring instrument does, the ADU100, is it sends out a small microamp current, and it can use that current to measure and calculate the lead resistance of the wire, and it can subtract that out to ensure that the temperature reading that's reported is strictly the temperature at the probe. So that's critically important with PT100 RTDs. Now, when it comes to wiring the RTDs, they use the A, the B, and the C terminal. And I mentioned just a minute ago that you have 3-wire and 4-wire RTDs that are available. They're wired identically, except with the 4-wire RTD, you simply tie off that 4th lead. Now, there are some measuring instruments, some very high-end, generally scientific measuring instruments that will take advantage of that 4th lead fully, but you don't find those very commonly in industry. Next, let's talk about that diagram at the bottom there, and that is a 2-wire sensor. What's that all about? Well, that's actually a PT1000 sensor that doesn't have 100 ohms at 0 degrees Celsius, but has 1,000 ohms of resistance at 0 degrees, which means that in general, the resistance values are about 10 times of what you'll find with a PT100. So because those resistance values are so much higher, then the lead wire resistance is really just round off error that isn't significant, and so a 2-wire sensor is appropriate. Now, one thing to mention about PT1000 sensors, and you'll see that on the next slide, they have a much more limited temperature range. In many applications, you'll be tempted just to use standard RTD lead wire, or even just copper wire, between the probe and the measuring instrument, or the ADU100. Now, if you've got an application with a fair amount of noise, I would recommend that you opt for shielded RTU lead wire and properly ground the shield, of course, to eliminate EMI and RFI in your application as much as possible. So again, if you think there's electrical noise around, you're doing some heating or something at some higher voltages, I would encourage you to use shielded wiring as well with RTDs. Now, in terms of the temperature ranges that are supported of PT100s and PT1000s, you can see there on the screen that the PT1000s are much more limited in terms of their temperature range. Now, in terms of the format in which the temperatures come back, you can select in configuration between degrees Celsius or degrees Fahrenheit, and the values come back already in 10th degree increments. Now, from an RTD LED standpoint, if you have an open circuit on your RTD, your LED, your status LED and the module will turn off. Now, something I neglected to mention with 4 to 20 milliamp and 0 to 10 volt, that LED will be on with 4 to 20 milliamp or 0 to 10 volt if your reading is above 0, or basically above about 0.2% of 0, then that LED will be on in the case of milliamp or voltage. Next, let's talk about thermocouples, another type of temperature sensor. And these were some of the earliest temperature sensors used in industry. They have the advantage of being relatively inexpensive, and they have the widest temperature range possible, but they are a little bit tricky to deal with, which keeps them from being applied in a lot of different applications, and they can be susceptible to electrical noise, and you'll see why here in a minute. How do thermocouples work? Well, thermocouples take advantage of the material properties of metals. If you take two different metals and you join them at the tip, at the point where they're joined, a voltage will be generated that varies with temperature. So that tip, called a hot junction, can be used as the measuring point for your temperature, and it will generate a different voltage as the temperature changes. One thing to consider, though, is that the voltage generated is very small. It's only in the millivolts range, okay, a few millivolts or so. And because that is such a small signal, relatively speaking, that's one of the reasons why thermocouples can be susceptible to electrical noise. Now, another factor with thermocouples that makes them tricky to deal with is that when you take each lead of the thermocouple and you connect it to your measuring instrument, the ADU100 in our case, then you're also going to have a small voltage that's generated at those points, which is effectively error. So any quality thermocouple measuring instrument, like the ADU100, must measure the temperature at what's called the cold junction and calculate what that voltage loss is and compensate for that so that the resulting reading that's reported is strictly the temperature at the hot junction or the tip of the probe. So that's a couple of the factors that makes thermocouples tricky to deal with. Now let's talk about wiring and our application tips. Okay, on the right there, you can see that thermocouples are wired to the ADU100 using the A and the B terminal. And there's two different types of thermocouple construction. You have what's called ungrounded thermocouples and grounded thermocouples. With an ungrounded thermocouple, the tip of the probe, or the hot junction, is electrically isolated from ground. So in other words, if that tip physically comes into contact with the machine or the measuring point, and that machine, let's say, is a chunk of metal that is somewhere earth grounded, if you've got an ungrounded thermocouple, your probe is isolated from ground. Whereas with a grounded thermocouple, there is no electrical isolation between the measuring tip and the probe itself, so that if that probe itself touches earth ground, then you're going to have ground potential at that point. So that's the difference between ungrounded and grounded thermocouple sensors. Why is that important? Well, not every measuring instrument can handle both types of sensors. Now, the ADU100 can handle both ungrounded and grounded thermocouples, but there are other products from other manufacturers and even some products from Horner that don't support both. For instance, the Smart Rail thermocouple module only supports ungrounded. The Model 6 I/O option for the XL series and the XL Prime, it only supports ungrounded. Whereas, for instance, the Model 5 XL series I/O option and XL Prime I/O option supports both, and Smart Block thermocouple supports both as well. Now with thermocouples, when you look at extension wire, that's another factor you need to consider in your application, and that is this. You might be tempted between the thermocouple probe and the ADU100 to use standard copper wire to connect the two. Bad idea. What will happen is you will get a cold junction out in the field where it can't be compensated for, and your readings will be way off. So what you need to do instead is use thermocouple extension wire between the probe and the ADU100. And that's true with really any thermocouple measuring instrument, not just the ADU100. So if you're using a Type K thermocouple probe, you should use Type K extension wiring. And if you have a noisy environment, you should use shielded thermocouple extension wire and properly handle the shield. Remember, we're only talking about a signal that's a few millivolts in magnitude. Next, let's talk about the signals or the values that are being reported by the ADU100. Those values are going to vary by thermocouple type, at least the range of values that are supported. And you can see on the screen there 8 different thermocouple types that are supported by the ADU100 and the temperature ranges that are supported in both degrees Celsius and degrees Fahrenheit. And then in the red columns, you will see the decimal values that are reported by the module if you have an open circuit condition. And in generally, well, always, those values that are reported are larger than the highest range value that could be reported for that thermocouple type. Now, the values are, just like RTDs, already scaled for temperature in degrees Celsius or degrees Fahrenheit increments. From a status LED standpoint, the thermocouple module only turns on the LED if that channel is enabled for thermocouple. So you can't really use that LED for detecting an open circuit or anything. That's going to be based on the readings coming back that you're going to detect an open circuit. Okay, now let's talk about millivolt input, which is supported by the ADU100. What are millivolt inputs typically used for? Well, the most common application would be load cells. Load cells are force transducers. So they are mechanical devices that convert force, which could be load, weight, tension, etc. They convert force to an electrical signal, which can be measured. Sometimes you'll hear the term strain gauge being used. Well, strain gauges are actually internally part of the construction of the load cell. A load cell is actually an array of strain gauges. Now let's dive a little more deeply into how load cells work. So electrically, a load cell is based on a Wheatstone bridge. And all those little resistors you see there, those are effectively strain gauges, individual strain gauges. Now, the way a Wheatstone bridge works is that you have something called excitation voltage, which is the input voltage for the circuit. And that might be, let's say, 10 volts. So that 10 volts of excitation will excite the circuit, and then based on the gain of the load cell, or the Wheatstone bridge, the output voltage will be generated. What is the gain? Well, the gain varies by load cell, but it's typically something on the order of, let's say, 2 millivolts per volt or 3 millivolts per volt. So the magnitude of the output of a load cell is going to be the excitation voltage times the gain. So in the case of a 10 volt excitation and a 2 millivolt per volt gain, you're going to end up with a full scale output of 20 millivolts. So what does that mean? Well, let's say you have a load cell that's measuring 0 to 100 pounds. And if your excitation and gain are as I have it on the screen there, then 20 millivolts will represent 100 pounds, 10 millivolts, 50 pounds, 0 millivolts, 0 pounds, that sort of thing. So that's how load cells work. And as you can see, those are some pretty low signal ranges. Now, is the ADU a good choice for load cells? With the ADU, you have effectively a 0 to 60 millivolt input range is the only millivolt range that's supported. So is that appropriate for a load cell application? Well, the answer is it depends. If you have an application that requires very high update rates and very high resolution levels, then you're going to be better off with a dedicated load cell interface, a dedicated piece of equipment that's going to interface with your load cell and is going to come up with the reading that you can then pass on via another signal type or a industrial network or something back to the OCS. However, if you have routine requirements, you're doing some weighing, you don't need especially fast readings, you don't need readings with crazy amounts of resolution, then the ADU100 will be a good choice. Now, one thing that can happen with load cells is that it is possible that your excitation voltage, that's the input to the load cell, it could drift. Now, generally with load cells, you're going to be selecting an excitation supply with really good specifications so that you get a good constant voltage that doesn't drift. But if you have concern about voltage drift of your excitation, you could connect your excitation supply to another channel of the ADU100 and measure that voltage, as long as that excitation voltage is 10 volts or lower. So that's one way that you can use the ADU100 to not only measure the output of your load cell, but also verify the excitation voltage. And if it does drift, you can compensate your reported load cell readings appropriately. Now let's talk about the way that values are reported back and also talk about something that I'm calling effective resolution. So if you're using a load cell range with an ADU100, you're going to select the 0 to 32,000 scaling range, even though some lower resolution ranges are available. That's just because that's the only real practical range available. And 0 millivolts represents 0 counts, and 60 millivolts is represented by 32,000 counts. Now, what is your effective resolution, though? So let's take a look at real-world applications with a couple of different load cells and, let's say, 3 different excitation voltage levels. So a couple common load cell gains are 2 millivolts per volt and 3 millivolts per volt. And some common excitation voltages are 5 volts, 10 volts, and 15 volts. So in those scenarios, depending on your combination, you're going to get an output that ranges anywhere from 10 millivolts up to 45 millivolts. Again, depending on the combination of gain and excitation voltage. And there in that fourth column on my chart, you'll see effectively how many counts you have over the entire range of the load cell in that scenario, because it's going to be a subset of 32,000 counts. If that number of counts is plenty of counts for your application in terms of the resolution you're looking for, that's another reason why an ADU 100 could be an excellent choice. And from an LED standpoint, the ADU 100 is going to turn on its status LED as long as a signal greater than 0.2% of the reading is present. So that's a walk through the different signal and sensor types available to connect to the ADU 100. Let's next do a demonstration of both how to configure the ADU 100, and then we'll do a little work on the bench as well. Now let's take a look at ADU 100 configuration in Cscape. So I'm in Cscape, got my project open here. And to do configuration on the ADU 100, we need to go to our hardware configuration area, which I can access from this icon, or I can go to the controller menu and select it from there. Next, I need to go to the CAN IO tab that contains my OCS-IO rack. And in a couple weeks, we're going to go through and from A to Z all the different configuration approaches for the CNX 116 or for OCS-IO in general. But today we're really just going to focus in on ADU 100 configuration. So we've got a complete rack here of OCS-IO. And I'll just quickly double click on the CNX base here so you can see how that was configured. We assigned it a name. It was assigned a network ID. We assigned a status register or status variable. And then we have to assign a starting IQ, AI, and AQ real-world I/O address for each of the 4 different I/O types for the base. So that's how that works. Of course, we'll cover it in tremendous detail from A to Z in a couple weeks. Today, we're focusing on the ADU 100. Okay, so in my rack of 8 modules total, including the CNX, I have 2 ADU 100s. Let's take a look at those now. We'll just look at one of them. So here are the different things that we can configure on a module by module basis. And that is, we have a filter, an analog filter, that can range from 0 to 7. The lower the value of 0 actually, is no filtering. And then as you increase up from 0, 1, 2, 3, all the way up to 7, you progressively get more stable readings that take longer to respond to changes. So it's a compromise between signal stability or reading stability and reading response time. So I like to start with 3 for most applications. It's a good middle ground. Okay, we're going to skip all the way down to the bottom now and talk about this one here, which is the input update time. And that is in milliseconds. It can range as fast as 10 milliseconds and go up from there. I've set it to 25 milliseconds. What is this? Well, this is how often the ADU 100 is going to send new readings over CAN to the OCS controller. So that's what that's for. So you can, again, adjust that for whatever speed you need. 25 milliseconds is a pretty good response time here. Okay, and then we have our channel by channel configuration for our signal and sensor type as well as our data range. So let's take a look at all those different signals that are available here. So I'll just pull one of these down here, and I've got on the screen here voltage and a couple different current options and 0 to 60 millivolts for load cells and all those different thermocouple types. A couple different RTDs, and of course disabling the channel altogether, because disabled channels will not be scanned, just so you know there. Once you select the actual particular signal or sensor type, then you can select a data range. Now for voltage, current, and millivolts, you have your choice between a few different ranges here. I always select 0 to 32,000. It just gives the most resolution. And then for temperature type sensors, we have our choice between Celsius and Fahrenheit values, and those come back in 10th degree increments. So that's all there is to configuration of the ADU 100. Now let's go take a look at the bench. Here's our bench setup. We've got our full rack of OCS-I with a couple of ADUs in the middle here. I've got my EXLW that I'm using for demonstration purposes. And then I'm using this handy dandy high-tech simulator to simulate all these signals that I want to show you. Now, I'll warn you in advance, my unit was not, my ADU 100s were not factory calibrated. So they're a little bit off, but for demonstration purposes, we should be fine. So let's start with 4 to 20 milliamps. I'm at a mid-range setting on my simulator of about 12 milliamps. So let's see what things look like. Mid-range would be about 16,000 counts, and we're there within a count or two. Looks pretty good. And I am kind of simulating a 10 to 100 pounds per square inch type sensor with a 4 to 20 milliamp output. If I go down to, say, 6 milliamps or so, which should be a fairly low setting, you can see my readings respond. If I go up to full scale at 20 milliamps, you see they respond as well. Now, the time it takes them to respond, remember, that's all influenced by the filter setting that we set up in configuration. So the lower that filter number, the faster it responds, the slower it responds. But again, we're also trading off on signal stability. All right, so now we need to switch to voltage range to show you voltage range. And I got to move my probes from the milliamp position to the voltage position, which I'm doing off camera here. All right, yep, they're definitely in there good and tight. Then I need to move my output of my simulator to the next voltage channel. And let me change my simulator configuration from milliamp to voltage, which I've done now. Let's go to, say, a mid-level range of 5 volts. And then let's take a look here. Obviously, I don't have a good connection. There we go. I have a little bit of trouble with these terminal strips. I won't tell you who the manufacturer is. But anyway, now that I've got a good connection, you can see mid-range, I'm within a few counts of 16,000. If we go down to, say, 2 volts or 20%, we should see it react appropriately, and it is. And I'm simulating here, say, a level of 0 to 1 meter, and at 20%, I'm at the 0.2 meter level. We'll go ahead and go up to a full 10 volts here on the simulator and watch it go up to 32,000-ish counts. Okay, so that's voltage. All right, the next thing I want to show you is thermocouple. So I need to add my thermocouple probe here to my simulator. Now, my thermocouple probe does not use these copper outputs here. It uses a special thermocouple extension wire type cable that connects to my thermocouple channel. Again, I need to switch my simulator offline here from voltage to thermocouple. I've done that. Let's say go to 50 degrees Celsius, and let's take a look at what it looks like on the screen here. There we go. Again, pretty close to 50 degrees. You can see the counts is 10 times the actual temperature because it's in 10th degree increments, and I chose degrees Celsius here. Okay, let's go ahead and go to 500 degrees. And you can see we respond based on our filter setting, and we're up to pretty close to 500 degrees. So that's thermocouples. Next, let's take a look at RTDs. So I'll disconnect my thermocouple probe here, and I'll change my simulator from thermocouple to RTD, which I have done. And we'll go with a, say, 50 degree setting. Of course, I got to remember to move my probes. Okay, let's move them here. All right, got to get it in the right position, though. There we are. Hopefully those are in there good. We'll soon find out for sure. Let's go to RTD. And you can see we've had a little trouble with our probes there, but we're making our way down to 50. All right. And it's getting there. Now, the reason it's taken so long is it was basically an open circuit. So it was way up there at full range, and it's taken a while to get down close to 50. And again, my unit's not factory calibrated, so I'm not really all that close, to be honest. It's getting there slowly. Let's go ahead and switch it up to 500 degrees and then see if we can get up in the neighborhood at least. Yeah, we're getting up in the neighborhood. Again, this unit could really use some factory calibration on the RTD range for sure. So that's RTD. So I have one more range I want to show you, and that is millivolts. So I need to change my simulator from RTDs back to voltage. So let's make that happen here offline. You can't see it, of course. There we go. I'm on voltage. I'm going to set it for, let's say, 5 millivolts. And then I got to remember to move my probe to this last position here. Hopefully I can get a decent connection there. And let's take a look at 0 to 60 millivolts. Okay, so Again, we are sneaking in on 5 millivolts, and you can see our raw counts there. Now we're scaled 0 to 32,000 correlates 0 to 60 millivolts. So you can see I'm right about 5 millivolts. Let's go ahead and bump that up to 20 millivolts. We should see our reading respond, and it is. And again, we can go all the way up to 60 millivolts with this particular range, but with most load cells, they're going to be in the 20 millivolt or 30 millivolt range most of the time. So there's our millivolt range. So hopefully this demonstration was useful to you. You can see how versatile this ADU100 is. And again, I'll take my units in and get them factory calibrated so we can get the full advantage of the full 0.2% accuracy. So that's it from the bench. So hopefully this has been a worthwhile presentation for you of our versatile ADU100 OCS-I universal analog input module. It's definitely a versatile module that can connect to many sensor types. We gave you lots of application tips. It's versatile in the fact that you can select each channel on an individual basis. And we also demonstrated for you how simple and straightforward configuration is when performed in Seascape. Now, as Casey mentioned in the opening, later in 2023, you'll have an additional option with a Seascape upgrade that will allow you to change sensor types in the field on the fly. So if you have a company that does temperature control and some of your customers prefer thermocouples and some prefer RTDs, and you want to be able to change those in the fly in the field, today you can't do that. Today you have to have a different Seascape configuration for thermocouples and RTDs, but in the future, after that new version of Seascape is released, you'll have the ability to make that change in the field. We're celebrating 10 years at Horner Lighting, so don't forget to check out our lighting videos on the Horner APG YouTube channel. They're right up there alongside all of our great automation content. This is where I remind you we're here every Tuesday, either fully live or streaming live a pre-recorded video, always ready to answer your questions in the chat section. If you're watching this on replay like a lot of you do, give us your comments in the comment section and we'll get those answered just before you know it. Next week, we continue on with our OCS-I series, and we're going to take a look at the digital I/O modules as a whole. So lots of capabilities, lots of different options when it comes to digital I/O, and we're going to explore that next week. Okay, if you haven't subscribed to our channel yet, don't hesitate. It doesn't cost anything. We promise we won't spam you with a bunch of extra notifications or anything. If you do subscribe and you choose notifications, you'll be notified every time we go live or every time we post a new video. And over the past several months, that's been well over 50 or maybe even 100 videos that we've posted. Lots to choose from. Okay, so until I see you again next week, let's all get out there and do us some good.